So we've been working on this situation with the oil spill, and we have the rate of change function. That's what we were given, and we started with the fact that at 0.7 days, at the moment 0.7 days, the rate of change is constant at 9.68. And so that means we've got the red curve, but in the moment 0.7, for a very short time around 0.7, we're going to assume essentially constant, right? And for a rate of change graph, constant means horizontal, right? Horizontal. It doesn't change. Because it's a small enough moment around 0.7, we can safely assume that with very, very little error, okay? And then I said, suppose that we know the amount at 0.7, it's 13.15 total meters cubed have up in the first 0.7 days spilled into the ocean, okay? So you've got 13.15 meters cubed of oil at 0.7 days. Okay, so what I want you to do on your sheet of paper by yourself is I want you to develop the function f. This is impossible. Wow, it's really hard to do. Try that. Let's see if I can do that. I want you to develop v in the moment 0.7, meaning develop the function rule. So v sub x equals what in the moment 0.7? V sub x equals what in the moment 0.7? All right? I'll give you a hint. We've done this over and over and over and over again. That's your hint. Okay? Everyone do it. I want you to develop the function v sub x in this moment. And that function, what? It represents all correspondence points of number of days and total amount of oil in the moment 0.7. In the moment 0.7. Show all your work. Show all your work. You're working by yourself. This is a quiz. Should be developing the function v, which is the accumulation function, in this moment at 0.7. So in other words, v of x equals what? V of x equals what? Given the information that we have. So it's a function for all correspondence points of days and amount of oil spilled in this moment from around 0.7. Okay, let's take one more minute. One more minute. No calculators. No calculators. Okay, grade your own. We're going to grade your own. Okay? Get out something different. We're going to grade it. Get a pen or something. Okay, so we're going to make sure you're not changing your answer, first of all, and then we will spot check the grading to make sure that you're being honest and accurate. So be honest and accurate. First thing is we're going to where is it? Right here. Yeah, something different. So the first thing is, so you didn't have to do any graphing, but I'm just going to work through it on the graph because I think that helps. If you graphed it, great. But the first thing is this identification of this point, 0.7 and 13.15 as our reference point in the moment. We've got this number of days, and we've got corresponding volume of oil. Okay, so that's our reference point. And so how do we start this? How do we start? By finding we want to find every correspondence point in here and model that. Model every correspondence point. Well, somewhere over here, we just pick some unknown point. Say x comma v of x. We're in a moment, right? So we're in a moment. So what will all the correspondence points be in this moment? How will they be displayed? As what? Since it's constant rate of change. A line, right? It's going to be linear. We've got constant rate of change within the moment. So we're working on a linear relationship. Okay? And how do we build that linear relationship? First thing is, what comes first? Change x. Change of x. dx is, so we're going to go from our known reference point to any point x. If we're trying to model all the points, then we have to let that be variable, right? We let that point be variable. And so what is dx? X minus 0.7. Okay? And then, as x changes that much, the volume changes. How much does the volume change? Right. M dx, right? So we've got a change in x. That 9.68 means, given any change in x, the change in volume will be 9.68 times that change, right? That was our big theme in the first 3 weeks. So that dV is going to be 9.68 times that change in x. Finally, that allows us to find what Vx is, or what the y coordinate of that point. How do we get now the final value of volume, or Vx? Y initial plus the change, right? Or V initial, right? So we started with 13.15 initial, and we added the amount of change that we got for changing x from 0.7 to x. So it's going to be initial plus the change, 9.68 times x minus 0.7. So let's see. How should we grade this? If you just wrote that down and nothing else, 18 points. Okay? If you wrote down the work to get there, that's a full 20. Okay? So if you just wrote that down and then you didn't show any other work, that's still an A, 18 out of 20. Okay? If you showed the work to get there, then that's the 20. Now, in terms of if you didn't get that, so noting this initial correspondence point, that would be worth 2. Showing that dx was x minus 0.7, that would be 4. Showing that dv was 9.68 times the change in x, that would be worth another 4. And then somehow showing that v final was v initial plus the change would be another 4. So there's some partial credit. So like plus 2 for the starting point, plus 4 for change in x, plus 4 for change in y, plus 4 for the idea of this. If you didn't get that, okay? If you got that, it's at least 18, right? If you got that, it's at least 18, okay? If you didn't get that, here's how you can give yourself some points. 2 for the initial point, 4 for the change in x, 4 for the change in v, 4 for the idea of initial plus the change gives you final. Okay, give yourself a score out of 20. Score out of 20. Okay, so if you didn't do well, did my explanation feel familiar? We've got to get this. So I suspect that some of you probably still didn't get it, okay? But it should start to feel familiar now because we've been doing for several weeks now, okay? Change in x, corresponding change in y, or change in volume in this case, and then final value of volume is the initial plus the change. It's just the only difference in this case is we're just leaving that initial or that final x value to be variable. So we got to hold on to all our expressions. Rather than actually getting a number for dx, we hold it as x minus 0.7. Rather than getting a number for dv, we hold it as 9.68 times x minus 0.7. And then we add that to the initial, so that then that represents every correspondence point. That's what functions do, right? They give us all the correspondence points. All the correspondence points. So in blue there. Okay. Any questions on that? Not grading like how do I get my score. Just do your best to be fair and honest. But questions on the process or this example? Yeah. I'm not sure. The moment establishes a small domain where we're assuming it's linear. What's that? Write down what? Yeah, so this moment is from like 0.697 to 0.703. But we're just, no, so it's, yeah. That's less important than actually building the correspondence points. So these are the correspondence points. The moment, I'm just saying that's the moment. From 0.697 to 0.703. It's not part of the answer to the question I was asking you. Does that help? Okay. Other questions? Okay, do we, yes ma'am. So at one point on the quiz, yeah, I mean, yeah, because it's really, these are values of v. Other questions? Okay, so we'll turn those in. Okay, so we're going to build off of what you've done in your homework. We're going to stick with this example today. We're going to build off what you've done in your homework. So this is the rate of change of oil entering the ocean, as we know. And this is the accumulated volume of oil leaked in any number of days after the leak begins. And what journey are we on right now? We're on the journey of, you know how fast something is changing at every moment? In other words, you have the rate of change function. You want to know how much of it you have at every moment. Right? Accumulation function. Accumulation function. This is what we're going to be on this for another couple weeks here. We're going to be working on this, and in the next couple weeks is when it's going to get hard. Okay? Just warning you. And all this stuff you have to have down that we've been working on, or else it's going to fall apart. Okay? So, you know how fast something's changing every moment? Again, that's a rate of change function. You want to know how much you have at every moment. That's accumulation function. So our goal is, given something like the graph on the left, to build the graph on the right. So what did we just do? We actually just built a little piece of V, right, at 0.7. And someone put this in your calculator. So the piece of V that we found was from over 0.006. That was the width of the moment over 2.5 days. So no, let's hold off on that conversation for a second. All right, so this is more big picture stuff, more big picture. The key to developing the function V from the RV function we've seen is constant rate of change. How does this work? This works by, so we're given a rate in meters cubed per day, and what can we do with that? We can get dV equals mdt, and then from that, we can build V final is V initial plus dV, and we know, again, dV is the m dt. So this is this process we've been working on for a month. Working really hard on this. Okay, how does this fit into this idea that of our journey? You know how fast something is changing every moment. You want to know how much of it you have at every moment. So you know how fast something is changing every moment. You're given a constant rate, right? You're given a constant rate. And what does dV equal mdt give us? Not that. All right. Okay, here we were. Okay, so you're given a constant rate. Again, you know how fast it's changing. And dV equals mdt gets for us a little bit of accumulation, right? So given a constant rate, dV then is a little bit of how much you have, right? So that formula is the starting point for, given the rate, it gives you a little bit of how much you have. And then similarly, we go to V final and V initial. So that's the net or total accumulation. So you see how this process, starting here, start with the rate. Starting with the rate, we can get a little change, and then a net or total accumulated amount. Okay, so that's the kind of the big picture of what we're doing. Okay, so what did we do? And just what we did in the quiz. So we took the moment around 0.7, like a moment right here. And how wide was the moment we did? The width of that moment was 0.006. For the function we want has a total width of 2.5. So someone put that in your calculator and tell me, so let's multiply by 100 then. Okay? So I want to get a percent of the total domain that we found when we did that little quiz just now. We developed the function V for 0.006 days. So what percent of 2.5 days is that? What percent of 2.5 days is that? 0.24? And that was after you multiply by 100? Okay, so that little exercise we did for the quiz was 1/4 of 1% of V. We found that little bit of V, that little tiny linear part of V, but that was just 1/4 of 1%, or 1/400th. 1/400th of the whole graph. Okay? So we don't want to do that 400 times to build V. We could. So we could do that. We could build V one part at a time the way we just did. We'd have to do that 400 times, and we would have a pretty good pretty good model of V. We don't want to do that. That's going to take too long. Okay, so we're going to kind of step back and do a new approach to this. We know we want constant rate of change, right? We know we want constant rate of change. So we're going to go to your homework here. So what did we do? So you identified points. You identified points on the rate graph for your homework. Okay? And so every 0.4, right? And so these are those correspondence points represented exactly. And then I made my estimates just to the nearest whole number. Okay? So if you tried to estimate more to the nearest tenth, that's fine. I just made my estimates to the nearest whole number. So is this consistent with what you did for the homework? Did you do something like this at the beginning of the homework? Okay? So what did we say? We said doing what we did for the little written quiz we just had would take way too long. We'd have to do that 400 times to build the whole V function. So instead, what we're going to start with here is we're going to use these rates here. We're going to look at this first. Look at this first interval here from 0 to 0.4. And we're going to make that, we're going to call that a moment. Okay, that's a big moment, a really big moment. So from 0 to 0.4, we're going to make that a moment. And we need constant rate of change in our moment. So we're going to come up with a constant rate of change for that whole interval from 0 to 0.4, for that large moment. Okay, so what rate are we going to use? We're going to use the rate at the left side of that interval to be the constant rate for that whole interval. So that rate, RV of 0, which I've estimated to be about 28, we're going to call that the constant rate for the whole interval of 0.4 days. Huge moment, right? It's a huge moment. 0.4 days. Okay? And we're going to keep doing that. So in the next interval from 0.4 to 0.8, we're going to call a constant rate of change of what? What will be the constant rate of change in the next interval from 0.4 to 0.8? Approximately 17, or R sub V of 4, 0.4. And then similarly for the rest. So rather than zooming in until we know we have rate of change in a moment, we're going to kind of step back and do this a little differently. We're gonna chop up our rate function into big moments. So there's not so many of them. And now we're going to use this is a new function. This blue function is a new function that's like trying to be like R sub V. It's like pretend function. It's trying to simulate the curve R sub V. And we're going to call that R. We're going to just call that plain old R. So what is R? R is the approximate rate of change function. This is a new function created from R sub V that approximates the function R sub V. It's trying to be like R sub V. It wants to be R sub V. Okay? But what's the advantage to us? What is the advantage to R over R sub V? Why would we make it worse? We've got the exact rate function. Why are we making it worse? Why are we making it into an approximation? There's a huge advantage to this new function R. What is it? Okay. What is it about R though that we like? What's that? It's got all constant rates of change, right? It's got all. That's the whole point. This new approximate function R is all what? Horizontal display of points, which means constant rates of change in every one of these big moments. So we're going to start by working with R because that's the math we've been working on for the last month, right? Constant rate of change. So before we do that, though, we got to get used to this function R. So I want you to exactly and approximately rewrite each of these. So R of 0.5. R of 0.5. Here's 0.5. How could you express R of 0.5 exactly and with an approximation? So Similarly, r of 0.9. Here's r of 0.9. R of 0.2 and r of 1.1. I think I meant to go this way. So here, this is A, B, C, and D. So express exactly, in exact terms, express each of these dependent or values of r, and then approximately also. Okay, take a minute, think about that. When you're ready, talk to the people around you. Okay? So we're understanding what this new function is, the blue steps, the blue steps. Is r of 0.5 an ordered pair? And what is it? And what is it exactly? 0.5? Is it 0.5? R of 0.5 is? Is that what it is? Is that r of? Is this a point on r? I'm asking what r of 0.5 is. So how would you express it exactly? The blue graph is r. The blue graph is r, right? Okay, so we'll just do the first one. You can talk. What is r of 0.5? Expressed exactly. Expressed exactly. R sub v of 0.5, 0.4. When you say r of 0.5, you're saying what is the y value of this point? R is the blue graph. So we want, I'm saying, what is the y coordinate of that point? It's over here, right? So this is how we would just, over here is where we would describe r of 0.5. And where did that come from? Where did this y value come from? R sub v, the red graph, of 0.4. Doesn't make sense. R of 0.5 is R sub v of 0.4. Because this whole moment, from 0.4 to 0.8, we assigned what? We assigned the rate of change, the real rate of change at 0.4 to be the rate of change for that whole moment from 0.4 to 0.8. So R of 0.5 is going to be R sub v of 0.4, or approximately what? 17. Doesn't make sense. Really got to understand what that R graph is, the one that I have in blue. The steps, right? The steps. Okay, do the rest now. So do R.2, R.9, R1.1. Talk them out. Go. R of 0.2 is R sub v of for every value of x between 0 and 0.4, the R function has a value of R sub v of 0, right? We took that R sub v of 0 and we said we want that to be the rate for every x value from 0 to 0.4. So no matter what x value we put in here between 0 and 0.4, we're going to get the rate of R sub v of 0, a constant rate, approximately about 28. Right? It's 28 the whole way through here, 28. So no matter what x value I pick, the rate according to the R graph is 28. All right, R of 0.9. R sub v of 0.8. R of 1.1. R sub v is 0.8, same thing. Why? Because those are in the same moment. They're in the same moment, so they both have the same rate as the one we assigned to that moment, which was the R sub v of 0.8, or approximately 8. So we're just getting a feel for this new function R. It's pretending to be R sub v, but it's constant rates. And how do we get those constant rates? By the actual rate at the left side of the moment. We get each constant rate as the actual rate at the left side of the moment. And we make that the constant rate for the whole moment. Does that make sense? Really important. Okay, so now can we write this rate function? So we write this rate function. Well, it's in pieces. So we're gonna write. Let's see. Okay, so this is the R function. So this is our blue function here. I'll make it blue, so we're just so R sub x equals what? R sub x, R of x, R of x. So since it's in pieces like this, we're not going to have one rule. We're going to have we're going to have 5 rules. We're going to have 5 rules. Each rule is for its own part of the domain. So what's the first part of the domain? R of x. What is it? 0 to 0.4. Okay? And so when x is between 0 and 0.4, what are we going to make R of x? What is R of x when x is between 0 and 0.4? Exactly. So exact representation. R sub v of 0. Whatever that number is. So the rule is that R sub x is just this constant value, R sub v of 0, whenever x is between 0 and 0.4. All right? Next one is between 0.4 and 0.8. Now this is going to seem a little bit weird, but you'll see why we do it later. So just hold on. But what we're going to do is, although we're using the rate at point 4 to be the constant rate for that interval, we're not going to assign it until just after point 4. Okay, so we're going to do less than x, and then we're going to do that all the way to point 8. So that seems a little counterintuitive. We'll explain it later. Okay, we'll explain it later. But just when we get past point 4 is when we're going to start with the new rate. And what is the new rate? R sub v of 0.4. Okay, finish this. Finish writing this function. This is the R function, and we need to write it with 5 different rules because it's 5 different pieces. And we got to tell it for what x values each rule applies. So you finish that up. Here are the different subdomains. These are our moments, right? These are on the right there. Those represent the 5 different moments that we're looking at. And remember, these are huge moments, right? For a while there, we were talking about moments that were really small, and that's eventually where we're going. But we're starting with really big moments. Okay, so from point 8 to point 1.2, what is our rate of change? Our R value? R sub v of 0.8. So this is, now you got the pattern, that's easy. And so now this way of defining the function should agree with those little practice ones we had. What was the first one? R, we wanted to know what R of what? R of, what was the first one? 0.5? So how would we use this now, this definition to find R of 0.5? We'd go where? So we'd ask, where is 0.5 in here? Well, 0.5 is this one, right? 0.5 is in this domain, and so if x is 0.5, then the value of R is R sub v of 0.4. And then later on we had 0.9. So when x is 0.9, you have to find the line that applies. So 0.9 is in this interval. Therefore, R of 0.9 is R sub v of 0.8. Likewise, R of 1.1 is R sub v of 0.8. So do you see how this defines all values of R for every value of x from 0 to 2? Questions on that? Okay, so now we got this function R, which is what? Our approximate rate of change function. We started with the actual rate function, the nice smooth curve, R sub v, and we just built what we're going to call the approximate rate function. Why do we like the approximate rate function when it's worse, right? So it's not the actual rate. It's worse. It's actually a bad approximation because of these big moments. Why do we like it? Why do we want it? Okay, I'm just asking, what is it about the R function that is convenient for us? Constant rate of change. It's constant rates of change that are trying to be like the actual rate function. We know the math of constant rate of change, so we want to take advantage of that to work with it. Okay? All that stuff you said was right. But you're just answering a different question. All right, so now let's build. So we're going to build what's called the function capital A. Okay, so the function capital A is the accumulation function that we get from the R function, not R sub v. All right, so now we're just going to focus on the R function, which is our constant rates over 5 moments. We're just going to use R to build the accumulation function which we call capital A. All right, so where R is the approximate rate of change function, capital A is the approximate accumulation function. It's approximate because it's built from R, not R sub V. Okay, makes sense? All right, how are we going to do that? So we look in this. So let's to do that. Let's find what accumulation of oil do we have at 0.4 days according to R. So everyone figure out what accumulation of oil do we have in the ocean according to the R function or approximate rate of change function. So I want to know at 0.4. At 0.4, what would the value of A of 0.4 be? Can you do it? Or write out an expression that would calculate that. So, and then we're going to go. So we'll go from there. So we're just going to get 1 point to start with, and then we're going to go from there. How would I get the total accumulation of oil at 0.4? Not according to the real rate function, but our approximate rate function R. What would it be? Yes, sir. Okay, so what are you using to do that? Yeah, that's right. What principle are you using to do that? No. Oh God, no. We haven't said anything about rectangles. Yeah. Is anyone seeing rectangles right now? There's no geometry involved here. There's no rectangles, there's no triangles. So if you've had calc before and you're envisioning rectangles, just somehow erase it from your mind. Whiteboard finger. Erase it, okay? There's no rectangles here. We're not going to put rectangles there. This is an approximate rate function. It's trying to be like R sub V. It's just these constant rates trying to mimic the R sub V function. We're done drawing on that graph over there, on the left graph. We're done with adding anything. So there's no rectangles. Back to this question. You said A at 0.4 was?
0.4 times R sub V of 0.
Can I put the R sub V of 0 first?
Sure.
And what is this about?
11.2.
I'm sorry. What idea is that about? What idea is... Yeah, that's MDX, right? So I want to know how much we've accumulated by 0.4. I've got a constant rate, and then the change in x. This is MDX, right? And so then you got an approximation. What was that approximation?
11.2.
All right.
R sub V of 0 is 28.
Yep, perfect. Yeah, if you use 28, we get 11.2. All right, so now we've got this point here. We've got 0.4 and 11.2. So now, for the second moment, from 0.4 to 0.8, I want you to build. So there's just like the R function, we're going to have these rules, 5 rules. And so we're going to work in the second moment now, from 0.4 to 0.8. I want you to build A of x for that moment. A of x for that moment, okay? So that's from 0.4 to 0.8 right here. So for this is the second moment right here. Build the function A of x for that second moment. Meaning we want all correspondence points of days x and corresponding accumulated amount of oil with the x values between 0.4 and 0.8. What's the rule for that? What's the rule for that? Everyone see if you can do it. So think about it, work on it, and then get help if you need help. second moment from point 4 to point 8. Just like what I asked you to do on the quiz. It's the exact same thing as the written quiz. That's your hint. You're going to do the same thing. You got 11.8 to start with. So you can any change in x in that moment.
You're right. You have to find your initial point.
Good. Those are just values. Those are just values. That's just how the amounts of change. Okay, so lots of you are making the change of x 0.4. But if you're writing the function a of x, then we want to let x vary through the interval so that it could be any value of x, not just the whole interval, okay? So that's why it's like the quiz, in that we're going to let, I don't know where this goes from here, but I'll just say here. Any point x, comma, a of x. If we want to model all the correspondence points in that moment, then we got to start with a point that's any value x and then a of x. Then, what's the change? Start with the change in x. dx equals x minus 0.4. What's the corresponding change in y? So this point, so inside the moment, right? So here's the moment. We're inside. So this is any value of x inside the moment, okay? X, comma, a of x. So the change inside that moment is the change from the beginning of the moment. So x minus 0.4, that's dx. What's the corresponding change in volume? Okay, m dx. What is m? Yeah, which one is it? RV of 0.4. We're in the second moment, so it'd be that. But we've already built this rate function r that has all those moments already ready, right? So they're already all lined up and ready to go. So we don't have to use r sub v of 0.4. We can just use r. R will automatically be right in every interval. So if we're in the second interval, it'll give us the right rate. Times our x minus 0.4. So now how do we get the final value of a of x? A of x will equal initial plus the change, which is rate times the change in x. See, if you use the change of just of all 0.4, then you're just calculating the whole change for the whole interval. We want to build the function. We want to get every correspondence point throughout that interval, throughout that moment. So we need to pick an arbitrary x in the interval. Our dx will be from 0.4 to x. Corresponding change in volume will be the rate times that change. And then we're going to add the initial, just like we've been doing, right? Final equals initial plus the change. Question, does it make sense? So now, see, that builds every single correspondence point now in that moment. Every single correspondence point, which is supposed to be a line. Okay, anybody have a question on that? Okay, so let's try to build the rest of this here. So we got 0.8. So let's go on to the third moment. In the third moment, what would it be for a of x? What would it be for a of x? So you're going to need to figure out what this is. Right? It's going to be what? The total accumulation. So this was the what? This was the initial amount of accumulation, 11.2, for the second moment. But where did we get it? We got it from the final amount of accumulation in the first moment. You see that? It's because this is what we did. We found out how much total accumulation we got in the first moment, right there by m dx. That was the 11.2. So that final amount in the first moment became the initial amount in the second moment. So same thing's going to apply here. How are we going to get the initial amount in the third moment? Meaning, how much total accumulation of oil do we have at 0.8 days? What total accumulation of oil do we have at 0.8 days? How do we get that? So you're going to find that out and then finish that line. So see if we can do it. Figure out what's your initial amount of oil at 0.8 days. It'll be the same as what? The final amount of oil at in the second moment will be the initial amount then in the third moment, and then we're going to continue to build the function here for the third moment. See if you can do it. Go. Okay, we'll come around. If we lost you or I lost you, please ask. If you're lost, please ask. Did you guys find that? Do that? What is it? No, that's not right. That's not right. 0.47. No, that's not right. Try that again. What is 11.2 plus 17 times 0.4? Could be about 20. 19, 18. 18 point, just 18 flat. Okay, so hopefully you calculated that starting amount in the third moment is around 18. It's all the accumulation we had at the beginning of the second moment plus the accumulation during the second moment, which would be MDX. 17 in the second moment times the 0.4. So it's initial plus the change due to the second moment gives us the final in the second moment, which is the initial in the third moment. Okay? Plus what? R of x times x minus 0.4. Is that right? No, this is now the change of x in the third moment. The change in x of the third moment would be x minus 0.8. How much change do you have in the third moment from 0.8? X minus 0.8. You got to think it. You're starting at the beginning of the third moment, which is at 0.8. So you're going to go x. X is going to go into that third moment. So the change in x would be x minus 0.8 times the rate, which would be r sub v of 0.8 plus what we've got so far, 18. Okay, quiz Thursday, practice quiz posted today.
So when you're
with the R of X and then the 0.4
So it's
of that rate in that that R.
yeah. So it's the same thing. So we had 11.2 at the beginning of the second one, right? So that's like y initial plus the change in y from the whole second one would be what and dx.
Yeah.
So m would be our sub b of 0.4, which was about 17. Dx would be 0.4. So that's just initial plus the change. Gives you the final, 18. Well, that becomes the initial in the next one.
Okay.
Yeah, so it's that same thing again. Initial plus the change equals final. Final in the second moment becomes initial in the third moment.
Okay.
Yep.
Julia told me she has a link to drop in her class and whatnot, and you're like this month's, but it's not showing up online. I was just letting you know I was going to shoot you an email, so I can get
Oh, you never got in?
Yeah.
Oh,
Yeah, because
I me a long time ago.
I've been going online. It says there's no openings. That's why I haven't.
You can't. You're out of the ad hoc period. You need. Yeah.
Right, talk to the Matt.
We need to do an override. I thought you took care of that.
No, I've been checking online every other day. And
No, that was during open ad hoc in the first week of class. We should have talked to you in the second week.
I apologize.
So just get an override for me. Yeah.
Sounds good.
So I was just wondering, like the function like R of X,
Yeah.
that's kind of like replacing what would be like an N
It's all of the blue constant rates as a whole function. Right? So the Rx function is giving us that whole blue function.
and then we're calculating A of 0.4 is equal to R of A of 0. Or is that just like another way of stating?
What yeah. What makes more sense to you? Is there another way you thought was right?
No, it's just like, could we use R sub B for all the other ones as well instead of using the function R X?
No, that was just to get started. So that thing was just to give us that initial point, 0.4, 11.2. Yes, I could have had Rx of 0, just R of 0, or R sub B of 0, because they're both the same according to that function. Right? So we define in that whole first interval, we define Rx to be R sub B of 0. So I could have written either one. I could have written that, or I took it off, but R sub B of 0 is the same as R of 0, R of 0.1, R of 0.15, R of 0.3, R of 0.4, right? It's all that constant rate. So yeah, I just was picking on, that's what someone said, so I wrote it down.
Okay.
But yeah, any R value in that first, R of any X value in the first interval is going to give us the same rate as that. The constant rate in the first. Okay, you're welcome. Oh, thank you. This sweet.
The raw answer, so I missed that. But actually, my answer was correct.
Okay. So what number was it?
Number 2.
Number 2?
Yeah.
So just send me a quick email. Just all you have to say is change my score on top hat number 2. That's all you have to do, and then I'll remember.
So how do you want us to enter in the quizzes? Because there's too many people for us to catch.
I think there's cheating.
There was cheating. We
So
just couldn't
let's-
catch everyone.
So you mean on the grading or?
Yeah. Well, and people like erasing, or like some people like rewrote it and then.
Yeah. So it was really. Actually, I did it more to see for you guys to gauge how they're doing.
Okay.
So let's just not
Okay.
no grades. I did really low.
The people that were honest were like some of them were in the middle, but yeah, most of them were pretty low.
Let's just not
Count it. Okay.
it, and you just have it for your reference.
Okay. Yeah, because some of the students were like, it says this, so this, that one, this, and it's beforehand. Like, yeah. So just FYI too.